Prime numbers are the numbers with exactly two distinct divisors. So what does that mean? Well, suppose let us take the number 7. Now 7 has exactly two divisors which are distinct, and they are 1 and 7. Let us take 2 for example. So 7 is a prime number. 2 has exactly two distinct divisors. They are 1 and 2. So 2 is a prime number. Let's take 1. 1 has only one divisor. So it does not have two divisors, and hence it is not a prime number. Another example of a co-prime number, basically that means that the number which is not a prime number is 4. 4 has three divisors, 1, 2 and 4, hence it is not a prime number. Since prime numbers have such a simple definition, we might be compelled to think that there must be a pattern which is obvious to find, and that we can predict that where will be the next prime or what exactly it will be. But it turns out that there is no such obvious pattern, and it is quite difficult to see patterns in primes. How to check if a given number is prime or not? Number is prime. So how can we check if a number is prime or not? Right. Suppose we are given a number n. The way to check if it is a prime or not is simply to check its number of divisors. If they are exactly equals to 2, then it's a prime, same as the definition. But are we going to go through all the numbers from 1 to n and check if they divide n or not, and then count all those divisors and see if the count exceeds 2 at any point? That would be very inefficient way to check if a number is prime or not. Another way that might come to our mind is to check until n by 2, since the largest divisor of any number could be n by 2. For example, the largest divisor of 100 is 50, except the number itself, of course. So that's the thing, but there is actually even better way to do it. We only need to check until square root of n. Now why is that? Why we can only get away by only checking till square root of n? It is because of one property of divisors. So divisors occur in pairs. For example, suppose a into b is equals to c. Now a and b multiplied make c. So this is a pair of divisors. They both divide c. A divides c and b also divides c. We can see that when we divide c by b we get a, and when we divide c by a we get b. So divisors always occur in pairs. So to give you an example, let us consider 100. Now the first divisor of 100 is 1. its corresponding pair would be 100 by 1, that is 100. So this is a pair, right? Second divisor is 2, corresponding pair 50. Third divisor is 4, corresponding pair 25, and 5 corresponding pair is 20. Then 6 does not divide, 7 does not divide, 8 does not divide, 9 does not divide, and 10 divides, and corresponding pair is 10 itself. So A and B could be same as well. Now we can see that what this does is divides the pairs of divisors in two parts. Let us call this part A and B. Now we can see that if we multiply this and this, we get this. We multiply this and this, we get this. So we divide these divisors here, right in the middle. Now what can this maximum value be? So basically what I'm asking is, what can this value be maximum possible? Exactly at the middle. It would be such that when it is multiplied by itself or its corresponding pair, in this case the number of divisors are 9, that's odd, and hence we are getting 1 in the middle exactly. So it is multiplied by itself becomes 100, right? So what multiply by itself makes a number? That's square root of that number, right? So maximum value at middle could be square root of n, right? So if we check all the numbers from so 1 always divides every number, and we know that count would be 1 at the start because 1 always divides all the numbers, right? So we need to check from 2 to this middle half, that is square root of n. So 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we need to check the divisibility of this number by all these numbers, if any of them divides this number, then that number is not a prime number, because then the count will increase to 2 and the number itself always divides, right? The number itself always divides itself, so count would become 3, and hence that would not be prime number. So we need to check the square root of n. Now why we don't need to check these divisors? Why we don't need to check divisors above this number is because these numbers were in pairs. So if we have checked for divisibility of 2, let's say if we have checked the number 3 for example, and 3 does not divide 100, then there won't be any pair corresponding to that number anyways. So we don't have to check the numbers about this line, right? And if there is a divisor here, then there will be a pair on the other side, right? So it just doesn't make sense to check about this line, right? Now what if this is not exactly what we can square number, right? Suppose 90, then we need to take the integer part of square root of n. So integer part of square root of 90 would be like 9, because 9 into 9 is 81. Next square is 100, so it lies between 81 and 100, so we take n 9. So we only check till 9, so 1 and 2 to 9. If any number does not divide 90 from 2 to 9, then it would have been prime, but we can see that it does divide, so it is not a prime. Let us take an example of 37. 37, we would need to check it till square root of 37, right? The integer part of square root of 37 is 6, right? So we start checking from 2. Does 2 divide 37? No, it doesn't. Then we check 3, 4, 5, 6, and we conclude that this number is a prime because this does not divide 37, right? So this reduces our work by a far. We only need to check square root of n numbers. So thank you.